This slide is going to introduce one simple concept, okay? And it comes from the fact that the compounds dissociate. And we got to think about what dissociation actually means. What does the term dissociate mean? Simply. Yeah, it breaks apart into ions. Okay, so it's just a fancy word for saying it breaks apart. Okay, and so this says, what are the molar concentrations of each of the ions present in a 0.025 molar aqueous solution of calcium nitrate? Okay, and so the molar concentrations of each ion. Well, first off, we need to know what calcium nitrate is. Okay, every time I create a compound from a word, I do some scratch work. Calcium, Ca, what is its charge? 2 plus, okay. Nitrate, what is it? NO3, what's its charge? -1. So when I make this compound, I have calcium nitrate. Okay. All right. Is calcium nitrate aqueous? The rule says all nitrates are soluble except for what? Nothing. So it is soluble. It is aqueous. Not Ag, Aq. And so it will break apart into the ion calcium plus 2. I have one of them. It is aqueous. Plus nitrate ion -1. It is aqueous. And I have 2 of them. Okay. The thing I know about this solution is this. I have 0.025 molar concentration of the whole compound. What is the molar concentration of the calcium once it's broken apart? How many calciums come from the whole compound? Only one. So it has this much molarity. Okay? It's the same because I break from 1 into 1. How much do you think the molarity is for the nitrate, though? Times 2. Because for every one compound that is concentrated at 0.25, I'm going to make 2 nitrates. Okay? Another way to do that, that's just thinking about it. Mathematically, what you would do is this. If you do start off and do a conversion factor, okay, the molarity of calcium nitrate, you can say that for every 1 molarity of calcium nitrate, I get 1 molarity of, I'm not going to put equals. I don't know why I put equals. I'm going to get 1 molar concentration, of the calcium ion, and I'd come up with that number, or 0.025 molar calcium nitrate times, for every 1 molar calcium nitrate, I will get 2 molar nitrate ions. That has a, not 2 plus a, 1 minus. This would be what I have done is I have either have a ratio here of 1 to 1 based upon the compound. For every 1 compound, I have 1 calcium 2 plus. And in the case of nitrate, for every 1 compound, I have 2 nitrates. So I got a ratio from the compound itself. The other ratio I can get is from a balanced equation. In this case, I don't have a balanced equation, I just have a compound itself. Okay? And so molarity of the whole now becomes molarity of just nitrate. All right? So that can be thought of simply in terms of thinking about what happens when things dissociate, or you can mathematically calculate how much that molarity should be. Okay. Most of the time, we're using molarity as a conversion factor. Okay. And so it says how many grams of sodium sulfate are in 15 milliliters of a 0.05 molar sodium sulfate solution. In the A portion, we have two numbers, mils and molarity. So it looks like we might have two starting points. But remember, any number that has 2 units associated with it is a conversion factor almost all the time. This right here, you need to remember, is can be substituted for what? Instead of big M, it could be what? Moles over liters. Okay, so that is going to be a conversion factor. So our starting point is 15 milliliters. And this is of sodium sulfate. Okay. Now, I need to go to grams. Okay, but to go to grams, the only thing I can relate grams to is moles, and I don't have moles, but I have a conversion factor that has moles per liter. So can I use milliliters in this calculation? No. What do you have to change milliliters into? You have to change milliliters into liters. Okay? So that, hate that. 15 milliliters of sodium sulfate times milliliters to liters, so that I can use the conversion factor that has liters and moles. Okay? That is the molarity. In this case, for every 1 liter of the solution, how many moles are there? 0.5. Okay? And that is still all sodium sulfate. Okay. I don't want moles. What do I want? Grams. And then I have a conversion factor that says that in every 1 mole of sodium sulfate, there are a certain number of grams of sodium sulfate. How do I calculate that? The molar mass. And on homework, you go to the molar mass calculator, but on the test, you look at the periodic table, and each sodium weighs 22.99 times 2. A sulfur weighs an additional 32.06, and then oxygen weighs 16 times 4, and that comes up to 142. The reason I knew that was that several slides ago, sodium sulfate was given, and so I just remembered that. I didn't do that in my head, like right this second. All right. What is the conversion factor? What number goes with a milliliter? 1. And what number goes with the liter? 1e to the what? -3. In this case, milliliters are canceled out, liters are canceled out, moles are canceled out. I'm left with grams. This is the molarity, and this is a molar mass. Those are conversion factors that we use. All right, and I'll end up with grams. All right. In the B's case, how many milliliters of 0.5 molar sodium sulfate solution are needed to provide 0.038 moles of this salt? Okay, the molarity is going to be a conversion factor. So I start with the other number, 0.038 moles. Okay, I want to go to milliliters. To change from moles into volume, the molarity is used. So moles per liter is used, and that's the conversion factor. In this case, the conversion factor says 1 liter is 0.50 moles. And do I want liters? What does the problem ask us for? Milliliters. And so a liter can be changed in milliliters very easily. You said 1 milliliter is 1 e to the minus 3 liters. Okay, and so moles cancel out, liters cancel out, and I'm left with milliliters. I used a conversion factor here of molarity as a conversion factor. I didn't have to use molar mass because I didn't go from mass at all. Okay? Almost every one of these types of problems can be solved using just conversion factors. And you progress that way. Here is the new concept, okay, in terms of dilution. And you did this. You went into lab and you measured out red dye number 40, right? It was powder. And you went to the balance, you measured it out, and you dissolved it in some sort of volume of liquid, right? And you knew it was concentrated because you could see the color, okay? Most of the compounds that we have don't actually have a color, they're clear. But there is a concentration of things floating around. In this case, the dye, we could see it. If we wanted to create a dilute solution of that dye, what did you do? You had the stock, you had what was really concentrated, and what did you do? You took a little bit out, right? Put it into a different test tube, and then you added what? Water. Okay, this is what is physically happening. If you have a solution that is concentrated and you take out a small amount, what you're actually taking out is a number of moles or an amount of the, in this case, dye, and you put it in the test tube. The amount of dye doesn't change, okay? But when you add water into it, the volume does change. And so what you do is you make the amount of moles stay constant, you change the volume, and when you do that, moles divided by volume, the dilution or the concentration goes down. Okay? And so that's what we're going to do. Now, what functionally is this important to? Okay, when you are working in lab, you use mainly, let's say, very dilute concentrations of acid. That means a little bit of acid and a lot of water. But when we buy it from the company, we don't buy a very dilute solution, okay? We buy a very concentrated solution because when they ship it, we want it into as little water as possible so that we don't have to pay for a bunch of water to be shipped out. So we get a bottle that is really, really concentrated because it weighs less and we get more acid. But we never want you to work with that concentrated acid. So what we do is we take a little bit of the concentrated, add a bunch of water, because water is a lot cheaper, and then we let you work with that. And so it's functionally good for us to do that. And so in laboratory, we do a lot of dilutions where we have what are called stock solutions that are really, really concentrated, and then we make dilute solutions to use because we can store a lot of material in very small volumes, much easier on the shelf than if we made up 10 liters that we're going to use. We don't want to put 10 liters on the shelf. I might want to put 500 mils on the shelf of a very concentrated solution and then make up the 10 liters for you to use during laboratory. So it is actually used quite a lot. To do this, you've seen this calculation. M1V1 equals M2V2. Or the molarity at the beginning or initial, the volume at the beginning initial, the molarity at the end or final, and the volume at final. So you will see MIVI equals MFVF or M1V1 equals M2V2. What this will tell you is the starting molarity, the ending molarity, the starting volume of the solution, and the ending volume of the solution. But there's one more step. You've got to think about what in the world you do with those numbers. The mathematics here is very simple. You'll be given 3 of the 4, and you solve for 1. But then you've got to interpret what that means. So here is a problem. Okay? Make a 250 ml solution of a 0.2 molar hydrochloric solution from a 5 molar solution. Okay? At the beginning, I have is the M1V1 equals M2V2. At the beginning, I have 5 molar, the big. V1 is, I don't know how much of the 5 molar I need to take out, but at the end, I want the molarity to be 0.2 molar, and I want it to be 250 mils. Okay, mathematically, divide this by 5. Mathematically, divide this by 5. That cancels out, the molarity cancel out, and what I end up with is mils. Okay, I'm going to write it here. V1, the volume 1, is going to be in mils. And when I do that calculation, mathematically I get a value of 10. All right, so if you think about that, that's not the end of the problem. That's the end of the math. It's the beginning of thinking. Okay? That's where we all mess up, right? I can put things in the calculator, get the calculator, but what does that 10 mean? All right, at the end, how much volume do you want? Total. The problem says it should be a solution of what volume? 200 and what? 250. I start off with 10 milliliters of the concentrated. I take 10 mils of the 5 molar concentration, put it into a beaker, and then to get up to 250 mils, how much water do I need to add? 240 mils. Okay? So just doing the numerical calculation doesn't finish this. You've got to think about what you need to do to finish creating that solution. Usually you take a very small amount of the concentrated, put it somewhere special, and then add water to get it up to the final volume that you calculated you wanted it to be. You do not add 10 mils and then add 250 mils to that, because then you would have a total of 260 mils. The concentration would not be right. Okay? And so you have to think about what you want to get to, and whatever you add together must end up being the right volume that you wanted to calculate at the end. Okay? So very simple math, but you've got to think about what it means. Okay? How many milliliters of a 0.3 molar sulfuric acid are needed to make 450 mils of a 0.1 molar sulfuric acid solution? All right, if I help you, M1V1 equals M2V2. What is M1? Okay, in this case, usually the volume, the first one is the concentrated one. Okay, mathematically, as long as you match them, it doesn't matter, but 3 molar is what I start with. That is the concentrated. Okay, what is V1? That's the unknown. That's what I'm trying to solve. What is the molarity at the end? The 0.1. What is the volume at the end? 450 milliliters. How do I solve this mathematically? Divide both sides by? Not 3 molar. Remember, we do have to take care of units. All right, and if I get my handy dandy little calculator out, 0.1 times 450 divided by 3 equals, okay, to make the solution, what must you do? Describe it for me. Okay, so I'm going to subtract 450 from what? You got to take 450 minus 15. Okay, 15 mils of what? The 3 molar solution plus 435 mils of what? Water, because we're diluting, will create a 450 milliliter solution of a 0.01 molar dilute solution. Okay, so I calculated how much volume I had to take out from the beginning, 15 mils. That puts enough moles in the solution to get to my final volume, to final concentration, but then I have to add enough water so that it will get there. All right. I told you I teach one concept. The big concept is dilution. Titration is a terminology that really is just a concept you've already learned. Okay? Acids and bases react to form what? Salt plus water. It's termed a neutralization reaction. Okay? A titration is used mainly with, but not exclusively, but you learn it first by using very specific amounts of solution to neutralize acid and bases. So you'll put an acid in the burette, you'll have a base in the beaker, and you will react them until they're exactly reacted. Okay? But we've already done this concept when we did limiting reagent. Okay? Remember when you were asked to calculate, well, how much excess reagent was there, right? Okay? First off, you used one reactant and you found out how much product you could make. You started with the other reactant and you found out how much product it made. One of them ran out first, right? That's the limiting reagent. Okay? To find the excess reagent, what you had to do was go back to the limiting reagent and you had to calculate exactly how much of the limiting reagent will react with the excess reagent. So let's say sodium hydroxide and hydrochloric acid react. You found out hydrochloric acid was the limiting reagent. You had to go back and say, okay, if I start with my hydrochloric acid, how much sodium hydroxide did I need theoretically to react to make sure that I've reacted all the sodium hydroxide and the hydrochloric acid together? That is what we're doing with titrations. You can actually calculate exactly how much the two things need to react for them to be used up completely on both sides. Okay? And so we can do this calculation, and it's no different than what you've done before. You can have grams of A to moles of A, moles of A to moles of B, moles of B to grams of B. This is the same calculation, the same 3 multiplication steps for a limiting reagent. Grams of something to moles of something, molar ratio to grams of that. You're just relating two things and you're trying to decide exactly how much you need. Now, you can do them from the gram side, but we also now know that you can do it from a volume of reactant if you know the molarity of it can give you moles, and that moles can give you moles of B, and then you can actually calculate the milliliters. So instead of grams to moles to grams, you can also go milliliters to moles to moles, and then the volume. And so we're just calculating how much do you need to react completely one with the other. All right, look at this problem. Hold up. It's long, so that means it must be hard and scary, right? If it's more than one line, it must be the most difficult problem you have ever seen in your entire life. All right? If you read this, there's a lot of information given to you that really doesn't matter. Okay? One commercial method used to peel potatoes is to soak them in a solution of sodium hydroxide. Okay, I'll tell you this. That doesn't matter. Okay? Sodium hydroxide might matter. Okay? For a short time, I don't care. And removing them from the sodium hydroxide, I already know sodium hydroxide is going to be there, and spraying off the peels. Okay, who cares? It's kind of interesting, but does nothing for you to the problem. Okay, the concentration of sodium hydroxide, sodium hydroxide is something, is normally in the range of this to this. Okay, that's just background. All right, so the sodium hydroxide is analyzed periodically. Who cares? All right, one such analysis, okay, we started with 45.7 milliliters of this solution is required to react with 20 mils of this. What is the concentration of the sodium hydroxide solution? All right. So, got some starting points. And so, we know that 45.7 mils of this acid here is required to neutralize sodium hydroxide. All right. If I am relating sulfuric acid and sodium hydroxide, I'm going from one thing to the other. I need to know how they relate. How do I know how those things relate? What must I do before I do anything else? Or any reaction that we've been doing for the past 2 chapters? You must have a what? A what? How do you know how hydrochloric acid and sodium hydroxide react? An equation. So let's do the equation for this. The acid plus the base, because it's all about that. Okay, what does it make? Acid and bases create what? Water. And then whatever's left over, the ions. Okay, the cation is what? Sodium. That is the weirdest sodium I've ever written. Plus. And a sulfate is the anion, which is 2 minus, so I make Na2SO4. All right, have I told you the truth? No. I have to balance it. 2 sodiums on both sides. So I had 2 here, so I put a 2 there. That's cool. And now I have 1 sulfur and 1 sulfur. I'm hoping this works. All right. On this side right here, in this, how many hydrogens are right here? 2. How many are here? 2. 2 plus 2 is? Can I put something here to make that 4? What do I put? Good. All right. Now, I hope the oxygen works out. How many oxygens right here? 4. And how many more here? 2 plus 4 is? 6. How many here? 2. How many here? 2 plus 4 is? We're done. Okay, so now I can relate the two. All right. So, in this, what reacted? Exactly this many milliliters of this acid. Okay? All right. In this case, let's relate the acid to how many moles of sodium hydroxide we made. Okay? Because I know the equation, I can say for every one of these acids, I can react to sodium hydroxides. So if I start with that, I start off with 45.7 milliliters of the acid. Okay, that's sulfuric acid. I'm just writing A because it's easier. But can I use milliliters? Or do I have to change milliliters? I have to change milliliters into liters of the acid. Okay. And once I have that, I can determine, because of the molarity, 1 liter of the sulfuric acid gives me so many moles of the sulfuric acid. Right? Okay. And then I don't want to know how much acid I used. I really want to know how much what? Base I used. All right. And in this, I'm going to know that for every mole of the acid, I'm going to get so many moles of the base. Okay, from the balanced equation, what number goes right here? 1. What number goes right here? 2. From the information, what goes here? A 1. What goes here? The 0.5. What goes here? A 1. And what goes here? 1e to the what? All right, at this point in time, what am I going to end up with? What is my unit at the end of this whole deal at this point in time? Moles of sodium hydroxide. Did I want to know moles of sodium hydroxide? What did I really want to know? The concentration, and that's in molarity. So moles of sodium hydroxide have to be divided by liters of sodium hydroxide. Do I have liters? No, but I have 20 milliliters. So that will be the number of moles in 20 milliliters. And then what I have to change milliliters into? Liters. 1e to the minus 3. The minus 3. So, in this case, mathematically I would take 45.7 times 1e to the 3, e to the 3 minus, times 0.5 times 2 divided by 20 divided by 1e to the 3 minus. And I would come up with 2.29 molar sodium hydroxide. Okay, so what does that say? In this analysis, I had a molar concentration of 2.29 sodium hydroxide. Is that concentration useful for this process? Yes or no? What is the concentration of sodium hydroxide needed to be to peel potatoes? 3 to 6. I just analyzed it and said that I'm doing a lot of work, and what's going to happen? No peeled the potatoes. Okay? And so in this process, this would be somebody's job. They will take a sample out and they find out, oh no, the potatoes are not going to be peeled. So what do? They increase the concentration of the sodium hydroxide. And they may do this. They may calculate using M1V1 equals M2V2 how much concentrated solution they may need to add to get that up. That's someone's whole job. They get paid lots of good money to do that. And the whole job is something you learn in General Chemistry 1. An $80,000 a year job doing that. Not too bad, as long as you can calculate that. If not, you get fired. You just don't get points taken off your problem, you get fired. Okay? All right. And so we can do lots and lots and lots of practice. Okay? In this first one here, how would you prepare 100 milliliters of a 0.07500 molar solution of silver nitrate, starting from pure solute? All right, what in the world does that mean? Okay, there's a lot of words there, right? What am I actually asking you to do? What would you start with? If you're going to make a solution from pure solute, okay, pure solute is, the water is a solvent, the solute is silver nitrate, which comes in a bottle, which is a solid, okay? So I start the pure, I have to go to the stockroom, pull out the bottom, it says silver nitrate. It's an expensive bottle because it is silver, okay? And I need to make a solution that's 100 mils at that concentration. What do I start off with? Which number do I start off with? Okay, this is the important part of this, right? This is like a wonderful test question. I have two numbers. Which one is most likely a conversion factor? Molarity. Because that has 2 units, moles per liter. Okay. So, if that is the conversion factor, we start with what? The 100, right? So 100 milliliters. All right, 100 milliliters is all good and fine, but our conversion factor has what units? Moles and liters. Can I use milliliters? No. What do I have to do to milliliters first? I have to convert it to liters. Man, we've been doing that a lot, right? We said this was 1 and this is 1 e to the minus 3. Now we're at liters of solution, and by using the molarity, I can find out how many what? What can I find out using molarity? How many moles I have, or how many moles I need. And in 1 liter, I need 0.07500 moles, and all of this is still silver nitrate. Did I want moles? Can I go and measure out moles on a balance? No. What can you measure on the balance? Grams. And so can I change grams of silver nitrate into moles into grams? That is a conversion factor called what? Molar mass. And if I look up silver, okay, I have silver here is 107.87 plus nitrogen is 14.01 plus 3 oxygens is another 48. 169.88. Times 0.070 times in this case, this is the number. What does that mean? I've got a number. Tell me what I need to do. If you were next semester the TA in the lab, I told you to do this, and you did this calculation, and you have this number, what are you physically going to do? You're going to go to the balance, measure out 1.27 grams of silver nitrate. Then what are you going to do? Put it in some water. How much water? Be careful. You want a final volume of 100. So what you're going to do is you're going to dissolve it in, let's say, 90 milliliters. Because that 1.7 grams takes up a little bit of volume. If you added 100 mils of water to that, what might actually happen is the actual volume of the silver nitrate will make you go over 100. So what you do is you dissolve it in like 90 mils, make sure it's completely dissolved, and then you will fill it up until it gets to 100, so that it's absolutely perfect. Okay? And so if you do it in analytical chemistry, it better be perfect. If you do it for GChem, it's plus or minus 10% broken. Okay? And so mathematically we solve something, but that solution means something about what you're actually going to do. And so doing the math is one thing, but thinking about what that means is the next step that I want you to be thinking about. Okay? All right. So, next thing. Create a 250 milliliter solution of a 1 molar nitric acid solution from a stock solution that is 6 molar. All right. Is this a conversion type of problem? Or is this a different kind of problem? What kind of problem is this? A dilution. I started from a concentrated, want to go to a dilute. So, what is the equation for dilution? M1V1 equals M2V2. Which one is M1? What's the concentrated stock? 6 molar. What's the volume? 1 initially. What I'm looking for. What is the ending concentration you want? 1 molar. And how much do you want of it? 250 milliliters. Okay. 250 divided by 6. What does that mean? I got a volume. What does that math mean? You take 41.7 mils of the 6 molar, and I've just lost it. Okay, and you add 208.3 mils of water, and when that is totally dissolved completely, you will end up with 250 mils that has a concentration of 1 molar nitric acid.